A huge thanks to Brian for sponsoring this video.
Good morning, fellow mathematicians. Welcome back to another video. It's gonna be a fun one because it hasn't even been 15 seconds into the video until I have aggravated some of you guys. I'm gonna be brave here and I'm going to say that a circle is just an infinitely sided polygon. I'm gonna see myself out. On a serious note, though, this is one of my most favorite examples in my calculus class when the students ask, why do we need limits? Well, it's indeed true that a circle in an elementary geometry kind of way is not an infinitely sided polygon, but from a calculus point of view, we can make a nice connection between the perimeter of an infinitely sided polygon and the circumference of a circle, because those are going to be equal. I'm speaking of regular polygons at that. And this is what we are going to show today, and I hope you are going to enjoy the video. By the way, this video has been sponsored on the one hand by the wonderful people over on Brain. More information at the end of the video, please check them out, really helps out the channel a lot. And also by you guys over on Patreon. If you want to help the channel alive, help keep the channel alive, whatever, then please support the channel on Patreon. Would mean a lot to me, and it really helps me motivate to bring out new videos. And now we are going to dive right in. You can find a link down there in the description. So the first thing we're going to do is we're going to start off with a simple case of a regular polygon. Namely, we're going to start off with a square. Since we're going to take the limit as n approaches infinity, it really doesn't matter where we put our starting point for n being equal to 4, 5, 6 or whatever. But in order for us to spot a certain pattern, we are going to start off with a square. Nice and easy, fair and square. And at first, let us state what we want to show at the very end. We want to show that the circumference of a circle is just the limit as n approaches infinity, where n is the number of corners, okay, or the numbers of sides, those are equal on a regular polygon, of the perimeter, which is going to be a sequence with respect to n. This is what we want to show overall. And what is the perimeter of a regular polygon comprised of? Well, if it's a regular polygon, those are going to all be the same side length. And for n being equal to 4, for example, this is our base case, our starting point, we are going to get that the perimeter is nothing other than 4 times a. For n being equal to 5, it's going to be 5 times a, and so on. So in other words, we are going to get that this right here is the limit as n approaches infinity. As always, I'm going to denote it by capital L of a, which is going to be a sequence with respect to n times n. Because our side length obviously is going to depend on our regular polygon that we have. Why is that? Because if we were to inscribe the regular polygon inside of a circle, you are going to notice that on the one hand, for the circumference of a circle, we need the radius. So we are always going to put our radius in here. We are going to declare the point or the length from the center to one of the diagonal outer parts, so the corners of our regular polygon as r. And obviously our side length a is going to change depending on the case that we are going to have. If we have n being equal to 5, for example, it looks like this. And obviously a is going to be a different side length. With each and every iteration for n getting bigger, our side length is going to get smaller. And this is going to bring us to a whole other problem when it comes to the limiting process, namely a situation where we have infinity over infinity or 0 times infinity and the like. You're going to see. Stay tuned. It's a fun problem. Try it out for yourself, by the way, before watching the video. And now we're going to dive in with the calculations. And the first part is rather easy, because if we were to construct ourselves an isosceles triangle here, with the side length a here, we are going to just make use of Papa Pythagoras. So for n being equal to 4, the side length a is going to be the same as the square root of 2 times r squared, obviously by Pythagoras, square root of r squared plus r squared, which is going to turn into the square root of 2 times the absolute value of r, but r is obviously positive, since it's a side length in Euclidean space. This right here is the case for n being equal to 4. Okay, doesn't help very much because we can spot a pattern yet. What about n being equal to 5? I have drawn it out already. Let's make use of it. Once again, we are going to inscribe a triangle into here. From the center, we are going to get isosceles triangles out. And now we are going to get an angle alpha in here. It's not a right angle, obviously, anymore. And with this triangle, we want to get an expression for our side length A out. And you can make use of the law of sines, for example, or the law of cosines. I'm going to go with the law of cosines here because I don't know why the hell not. Both are equivalent, so that's not a problem. But in order for us to use the law of sines, we need a value for the angle alpha right here. And the cool thing about regular polygons is if we split this up, we can inscribe the same triangle 5 times into here for n being equal to 5. Meaning each of those inner corners are going to have the same angle. And since the full rotation is 360, obviously alpha is going to get the value of 360 divided by 5, which is going to be the same as 72 degrees. Or in other words, 360 is 2 pi divided by 5. Same thing here with the 90 degrees. This is the same as 360 divided by 4. So 2 pi divided by 4. This is just an expression for the pattern spotting that we need to do at the very end, you could say. Other than that, we can now make use of the law of cosine, which is going to tell us that a squared is the same as r squared plus r squared, so the side lengths, where the side lengths which are next to the angle between those legs, minus 2 times r squared, because we have 2 times r times the cosine of the angle between those two, so 2 pi divided by 5. And now what we can do is we can take the square root and bring some stuff together. R squared and r squared is the same as 2r squared. So we're going to get that a is the square root of 2r squared minus 2r squared cosine of blah blah blah. We can factor out the 2r squared times 1 minus the cosine of our angle. And now what we can do is we can once again make use of the property that we can break this up. R squared is obviously strictly positive and it's going to yield the absolute value of r, but r is positive, so it's just going to be r overall. And here we are going to get, if we break this up, the square root of 1 minus the cosine of 2 pi divided by 5. This is always positive because cosine is bounded by positive 1, obviously. So another problem with breaking up the square root. So a overall is going to be a square root of 2 times r times the square root of 1 minus the cosine of our itsy bitsy angle. And maybe you can see the first part of the pattern already. We are going to get square root of 2 times r once again. And if we were to generalize this for a certain angle alpha, we can also generalize this case a bit more for n being equal to 6. The only thing that is changing is going to be our angle alpha, its value. That's an ugly, not so regular polygon. Our angle alpha here overall is going to be, if we inscribe 6 triangles into here, isosceles triangles, it's going to be 360 divided by 6, which is the same as 60 degrees. So pi divided by 3 or 2 pi divided by 6, because 360 by 6. So with alpha being equal to 2 pi divided by 6, we are going to get that the side length A in this triangle is going to be, or on this regular polygon, square root of 2 times r times the square root of 1 minus the cosine of 2 pi divided by 6. And now I think all of you figured it out. Okay, it's really easy to spot what the pattern is going to be here. Our A must be a sequence with respect to n. And obviously our angle is depending on the number of sides that we are going to have. And it's very easy to see. For n being equal to 5, we are going to get 2 pi divided by 5. For n being equal to 6, we are going to get 2 pi divided by 6. For n being equal to 4, we are going to get, oh shit, it's actually not that hard. Square root of 2 times r times 1, and this right here is easy to see, is the same as square root of 1 minus the cosine of 2 pi divided by 4. Because 2 pi divided by 4 is the same as pi over 2, and the cosine of pi over 2 is going to be the same as 0. So we are going to get the square root of 1 and this is just 1. So all problems solved, right? So let us generalize this bit, and then we are going to solve our limiting process right here. A, with respect to n, our sequence is going to be square root of 2 times r times square root of 1 minus the cosine of 2 pi divided by n. It's as easy as that. Obviously, n element of the natural numbers without 0 and greater than 3 actually, but it doesn't matter, okay? Now we can continue our journey and we can solve this limiting process that we have right here. Let us take a look if it really holds that the circumference of an infinitely sided polygon is the same as, the perimeter of an infinitely sided polygon is the same as the circumference. I have been scolded in my last video because I said the circumference of a triangle, but that's not true. The circumference only defined for circle. I didn't know that actually. I knew the word perimeter, but I didn't know the differentiation. Yeah, I thought it was some kind of UK and US thing, but doesn't matter. Okay, you learn with your failures and that's good. So C is going to be the same as the limit as n approaches infinity of our sequence an, which is the square root of 2, times r times the square root of 1 minus the cosine of 2 pi divided by n, and all of this times n. And you're going to notice that square root of 2 times r is independent of n, so we can bring it to the front, and then we are going to be left with this square root term times n. And as mentioned before, we are going to run into a tiny little problem here when it comes to the limiting. It's actually not that trivial to show what the value of the limit is going to be. But the more sides we have, so for n to infinity, our side lengths are going to get infinitesimally small. This is easy to see because in the limiting process, it's continuous. We can drag it into the square root. Our cosine is continuous. We can drag the limit into the cosine. We are going to get the cosine of 1 over infinity practically, which is the cosine of 0 in the limiting process, which is going to go to 0. So what we are going to have is we are going to have a limiting situation of 0 times infinity. Or if you were to use L'Hopital, you are going to get a 0 over 0 or infinity over infinity situation. But here's a problem with Papa L'Hopital. We are only dealing with discrete values of n here. So 1, 2, 3, 4, 5, and so on. L'Hopital, strictly speaking, is only valid for continuous values of our sequence. So that's a bit of a problem. You can be a sneaky bastard and you can use L'Hopital here, and that's going to lead you to the right path because you are a little bitch. But we are not going to do that, okay? We are going to go about it in a tiny little bit more rigorous way. You could say it's a bit more clean. It's a bit more tight, okay? Looks better. And we are just going to make use of double angle formulas here. I don't know if this is cheating, but it makes life a bit easier. And you're going to notice that we have the cosine of 2 times pi divided by n. So let's take a look at the cosine of 2x double angle formula. That's the same as cosine squared of x minus sine squared of x. And those blah 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 squares just scream for the fundamental theorem of trigonometry, which says that cosine squared plus sine squared is the same as 1. So we can substitute our cosine squared for 1 minus sine squared, leaving us overall with 1 minus 2 times the sine squared of x. And now you're going to notice we are going to get negative our cosine of the double angle. So if we get a negative sign to the front, let us just ignore this part. And we are going to get negative 1 plus 2 times sine squared. So we are going to get a positive value obviously out under our square root. And the 1 and negative 1 is going to cancel out. So we are going to be left with the limit as n approaches infinity of n times the square root of the sine squared, and our x value in our case is going to be pi divided by n. What other thing do we have? Inside of the square root we are going to have a 2. We can break this up and bring the square root of 2 to the front. Square root of 2 times square root of 2 is going to lead to 2 times r overall. I hope you could see what I did here. And now the last things to do are to deal with what we got here. Now the square root of sine squared is going to lead overall to the absolute value of sine. Now you might think, oh no, absolute value, that's a tricky thing, but it's actually not. Since when n goes to infinity, everything's continuous, we can drag it to the inside once again, take the limit in here. Then we get sine of 0 overall in our process, and this is a positive value. So each and every iteration we get closer to positive in infinity, sine is always going to be a positive value, obviously. And since we started with n being equal to 4, for example, we also don't get a problem with the sine value. But we are only interested in positive infinity in the limit. So the absolute value is going to cancel out overall. And we are going to be left with what we got right here. And the last thing I'm going to do is I'm going to introduce a little substitution. Let par divided by n be equal to x. We are going to do a little substitution in here inside of our limit. Now, don't forget, this right here is the limit as n approaches infinity. So, what is going to happen here with our x overall? When n approaches infinity, it's just like with integrals, okay? It's nothing else. Then x goes to 0. So we are going to rewrite our limit as 2r times the limit as x approaches 0 of. Now n is the same as par divided by x. And then we are going to get sine of x. Now we can bring the par to the front. So the circumference, supposedly, is now equal to 2 par times r. Oh, there it is, and there it is. But we still have this right here. The limit as x approaches 0 of sine of x divided by x. And if you are the average anal enjoyer, analysis and calculus enjoyer, you might notice that this right here is a very famous limit that each and every one had to prove in some kind of way at university or at school. This right here is just gonna yield 1, and this is why I said this right here is the cleaner way in comparison to using L'Hopital illegally. And now we have shown that the perimeter of an infinitely sided polygon is indeed the circumference of a circle. And I think that is pretty cool, and I hope you did enjoy what you have seen today. And if you did, you should most definitely check out the content of today's sponsor, Brian, who were kind enough to sponsor yet another video here on this channel. Now, during the video, I have talked about a lot of things that you can take a look at geometrically very nicely, like the whole limiting process. The more iterations we do, the smaller our side length A gets. And taking a look at things like those graphically, like what happens if you add more and more sides to the whole thing, or it gets more and more circularly. That is the mission of Brain. This is what they want to show you over on their app, website, and just service in general. Brilliant is one of the most sophisticated online learning platforms that you can find out there on the internet. It really doesn't matter if you want to learn something about the mathematics that we did today, or maybe physics, computer sciences. Really doesn't matter. No matter what it is you want to learn in the STEM field, Brilliant definitely got something up their sleeve for you that you can use to learn something new on a daily basis starting today. And I'm seriously not exaggerating when I say that Brilliant is life-changing. And it has been life-changing to so many students and also subscribers that I have here on this channel. I did several live streams before, and just the majority of people are very keen when it comes to Brilliant. They have such highly intriguing visuals that you can play around with to get a better understanding of the problem at hand. And also graphics, which just get you a crazy good grasp of what is going on with, for example, limiting processes. What is happening when you do, for example, the double angle formula? What does it mean geometrically? What does it mean in a visual way? And it's kind of hard to explain how good Brilliant really is. And you should just give it a shot and check it out for completely free by using my link at the top of the description, brilliant.org/flammable. With it, as mentioned before, you are going to get free access to the whole landscape of Brilliant for completely free. 30-day free trial. You can also use my QR code up here or somewhere up here. I don't care. It's somewhere up here, maybe in both places now. But point is, you can try it out and see if it's something for you. And if you think like you would really benefit from Pre-in, even more if you go into some kind of long-term relationship with their services, then definitely make sure to make complete use of my link. And the first 20 people to do so get 20% off an annual premium subscription, which is an amazing deal considering how much content they already have available on the website and how much content they are adding on a regular basis. It's just hard to put in words how good of a service Pre-in provides to the whole STEM community. And you should just give it a shot and see for yourself how good it is in actuality. And this concludes today's video, and I hope you did enjoy what you have seen today. I really like this problem. It's pretty cool. And I wish you guys a flammable day. See ya.